All right, good evening, guys. My name is Ugenteraan. So today I will be talking about K-means. Before I start, can I know what your education background is, guys? Can you just tell me in the chat, or you can just unmute your mic and then just tell me as well? So we have one non-CS there. How about the others? Sorry? Non. Cornelius, how are you? I'm good, I'm good, I'm good. You're still working under Shah? Right. That's cool, that's cool. All right, cool. Nice to have you here. So, all right, we have a lot of non-CS people here. So, I'll try to keep the explanation as layman as possible, and then slowly goes to the mathematical side of it. Don't worry, there's not going to be much mathematics in this topic, but there's going to be some sort of mathematics will be there, and then slowly I'll go into the programming side of it. So, if you guys feel like if I'm going too fast, or like if you need more explanation on certain parts, do let me know. I'll try my best to clarify. But again, the flow is going to be from layman all the way to the programming, to the mathematics, and all the way to the programming, right? Don't worry, the K-means mathematics is not complex. It's just high school mathematics. The best, the most complex maths that we're going to be using is just the Euclidean distance, Pythagoras theorem. So those kind of mathematics. So there's no any kind of heavy mathematics will be involved here, right? Okay. So before we start, let's another thing. There's not going to be a lot of slides here. I'm just going to be showing you guys visualizations from other websites and my own notes and my own codes. So don't worry about the slide. That's just going to be one or two slides, right? Okay. So before we go into the details, let's start with a simple thought experiment, or if you want to call it that. So imagine right now, right? You are an alien. Okay. So you have never visited Earth before. So this is the very first time that you're coming in through the horizon, and you're looking down on everybody on Earth. Okay. So assuming that you are at a point of view where you can look at each and every human on the planet, right? Now, immediately with just one glance, you can group all these humans. We're not talking about animals, okay? We're just talking about the humans. So you can immediately group all these humans into different categories, right? I mean, you can obviously see, and then this group of people belongs to one group, this one belongs to one group, and so on. Now, the question is, how did you group them? What would you be basing them on? Come on, guys, give me some answers. You can just chat again, or you can unmute your mic and tell me as well. Let me check the answers. In general, no need to talk about gender yet. All right, the skin color is good. How about anything else? Height is also good. Any other factors? Remember, you're an alien, so you don't know much about the culture, the society, hair length. Okay, I mean, I guess so. Maybe one or two more answers. Come on, guys, is that all you can think about? Not really. You can still differentiate, even though you're first time saying it. You guys were in the right direction. Skin color, height. Language, yeah, but I don't think you can see that in the first glance, but okay, that's good. Facial age is, yeah, I guess you can group them by age, right? That goes to the facial age. All right, cool. So the other factors are probably eye color and probably the location. right? I mean, we all located at different parts of the earth, and normally, yeah, facial features as well, like the eyes, the length of the eyes, the shoulder width, um, uh, the jaw lines and stuff like that, right? So you see, with just one glance, even though you have never seen humans before, you are able to distinguish or group them based on these features. Okay, so now coming back to our topic. So these features are what defines data. All right. So data points, when we are talking about data points in machine learning or data science or AI in general, right? This is what we are talking about, the features. So each human can be represented via a data point, and each of these data point has these features that you guys told about: height, skin color, facial features, age, whatever, right? So skin tone, all these things are what defines our data point. Okay, so in this use case, again, remember height, skin tone, facial features. Okay, these three things are the determining factors. So we know based on our common sense that when we take all this data and then we try to map it in some plane, 3D plane or 2D plane or whatever, these groups of people that have similar features, they are going to be clumped up together at one point of the chart, right? I mean, obviously, if you take all the Europeans and then you chart them based on their height, based on their facial features, based on their skin tone color, they're going to be at one corner. If you take all the Indians, they're going to be at one corner. Chinese, one corner. Malays, one corner. So maybe some of these people share certain similarity. For example, I think maybe Chinese, Malay, and Indians share almost the same height kind of similarity. So they might, in terms of height, they might be together. But in terms of facial feature, they might be different, far apart. In terms of skin tone, they're going to be far apart. Now, in terms of skin tone, maybe Chinese, Malay, and Europeans are going to be at one point, right? I mean, clumped up together a bit. But in terms of height, maybe not. In terms of facial feature, no. So you see, even though some of these features correlates with one another, sorry, not the word correlate, not the word that I'm looking for. Even though they share some of these features, but other features might be different. So each one of these features are also known as dimensions in data. So we don't want to get too technical yet. It's just something for you to know, right? So enough about the data. So coming back to our thought experiment. So you see, when you view humans as data points instead of these complex organisms on Earth, things get simpler. Now, all of a sudden, you can group them together, even though the accuracy might be off. I mean, obviously, we have mixed race and people migrating from one place to another place and so on, right? So we are going to have some sort of trade-off with the accuracy there, but the general point stays the same. Okay. All right, now let's try and see how those data points gonna look like. Okay, so in a perfect world where Indians stay in India, Chinese stay in China, Europeans stay in Europe, and no mixed race or whatsoever, we're gonna have this kind of data, right? Okay, let's imagine just two dimensions: skin tone and facial feature, maybe. Um, Maybe not facial feature, maybe just let's go with height. Okay, so let's say this is height and this is facial feature, skin tone, right? So let's pretend that the skin tone can be digitalized: 0 for darkest, 1 for the brightest skin color. And then the height, obviously we have maybe from 100 centimeter all the way to 200 centimeter. Okay, so imagine that the axis is somewhere over here, right? So we might have Indians over here because the height is low and the skin tone is dark over here. We have probably Chinese or Malays over here because the skin tone is bright and the height is almost similar with the Indians. And maybe Europeans somewhere over here because their skin tone is maybe mixed a bit and their height is most often taller than the Asians, right? So Europeans here, Indians here, let's say Chinese here, all right? So we have these clumps of data together. Obviously, now it's super easy for us to see that this belongs to one group, that belongs to another group, and this belongs to another group. We, as an alien, obviously we wouldn't know that this is Indian, this is Chinese, this is Malay or European. Obviously those are the names that we give ourselves. It's just arbitrary, right? I mean, for all we care, we could have named us differently, and it's still the same thing, right? So for aliens, obviously this is group 1, group 2, group 3. Okay, now the only information that we need right now is how many group are we going to group these people of, right? So let's say, by seeing the data, we know that there's only going to be 3 groups, so we want to uh, group them with 3 groups. Okay, so as humans, obviously it's very easy for us to say that this entire data points is one group, this is one group, this is one group. But what if your data point is something like maybe something like this, or even maybe something like this. So you see, we know that this probably is just one group, this is one group, and this is 2 separate groups, or maybe just one groups, right? I mean, we know this is eyes, mouth, and the face, right? But obviously, how are we going to let the computer know that this is the problem that we are going to solve? Okay, so here comes the k-means. Okay, so let's just go back to our previous data set for easier explanation. Okay, obviously, like I said, as humans or as an alien, we know that these are 3 groups. But how are you going to write an algorithm or design an algorithm to let the software know that this is 3 different groups, and you want to categorize them into 3 different groups, right? So this is how we do it. All right, so the procedure is simple. First, we randomly generate a certain number of points. So we're going to call these points as centroids. Okay, so again, we're just going to generate 3 random points in this entire thing. So the point could be here, 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 or here, 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 or here, here, and here. Could be anywhere. Okay, so that doesn't really count. It could be anywhere. So that's the first step. Now the second step is we need to calculate the distance of each one of these data point to each one of those 3 centroids. So let's imagine our centroid was here, here, and here. So this centroid calculates all the distance between this data point, this data point, this data point. Same goes with this centroid and this centroid. Whichever centroid, whichever data point that is closest to centroid A is going to be belonging to centroid A. So probably this part of the centroid and this part of the centroid belongs to, data points belong to this centroid. The B takes maybe this part and this part. The C might take this part and this part. All right, so now we have these 3 groups of centroid. Now let me just add those centroid. So 1, 2, 3. So randomly those are the centroid that we get. Let me try and 1, 2, and 3. Okay, this is a bit better. So we have 3 centroid here, random centroids, right? So apparently the data points in this red region here identifies themselves as closest to this red centroid, and the green centroid is over here, and the blue or the purple centroid is over here. Okay, so now for the next step, what we are going to do is, now that we have this region, we are going to calculate the average of that region. Okay, average. So for example, for this green, in this entire data point, the average point might be somewhere over here, right? I mean, why wouldn't it there's more points on this right side than the left side, right? So it's somewhere over here. For the blue, I mean, it's already mostly dense, located in the right area, but there's still 2 centroid over here, so it might move a little bit closer to this area, or maybe move closer to the center over here. We might not know later. And for red, it might be somewhere over there, close to there. So when I press go, see this is what happened. So when we found the mean, the average, the centroid gets updated to the mean. Okay, so previously the centroid green was here. Now after calculating the mean, like I predicted, it's somewhere over here, so it went there. For blue, it went closer to the center over here because it's more densely packed. As for red, it didn't change as much. Now let's reassign again. Now now you reassign all the points to the closest centroid. Uh, for the red, because of the green centroid moving over there, these points became closer to the red color. And this point stays there. And these 2 points, earlier belonging to the blue, became green. So you see how it assigned themselves. Now, if I update again, it moves to their respective group again because the mean was there. So the mean is there. Now, when I try to reassign, nothing changed. When I try to update, nothing changed because it has already found its optimal place, right? So if it's too fast, I'll repeat this thing again. This is the procedure. So we first randomly generated a certain number of centroids, and then we calculated the distance between each data point and each centroid. After that, we assigned each data point to the closest centroid, and then we calculated the average or the mean of each cluster. We updated, and we repeated the steps. All right. Again, I added 3 centroid randomly, and then I reassign all the points to their closest centroid, and then update them to their mean, reassign them, update again, reassign them, and there we go. We have 3 groups. So now we have we have separated these data points to 3 different groups, and it's obviously what we have predicted earlier, right? With our human capability, with our human eyes, right? This belongs to one group, this belongs to one group, this belongs to one group. All right. Now this is what K-means is actually. Pretty simple. Nothing fancy going on. It's just basically calculating the distance, calculating the average, and then you reassign the points. That's it. Now, if you ask, what is the point of doing all this? Right? I mean, yeah, sure, we have them in groups. So what's so special about it, right? I mean, there's nothing fancy going on here. Here's the thing. Once we have all this group, let's say we already have this model, right? This K-means model with each of the centroid. We know the value of the centroid now. Now, imagine now you have a new person coming in. All right. So this person has a bit of features like an European, the skin tone and the height, but it's not that prevalent. Maybe a bit of an outlier. This person, right? So this person might be located somewhere here. Okay. Now, based on our calculation, which centroid does this person belongs to? Obviously, it's red because it's closer to the red compared to blue and green, right? So this person is an European. You see, that's how you do the grouping. Once you have this trained model, so-called training, I mean, what we did through just now with the procedure is so-called the training part of the process. So once you're done with this training, now when you deploy this into the real life, you can now use these 3 centroids to figure out what the person, which group the person belongs to, this new person. Okay, so that's how we use the K-means in real life. Now, I'll give you one more example. Imagine an anomaly detection model, right? So let's say that you are spending your credit card every day, and most of the time your routine is going to be the same, right? I mean, you're gonna use the credit card to buy grocery, to buy maybe do some online shopping, things like that. So when you do that way, based on the data, the features that they've been collecting on you, your pattern can be plotted in a graph, something like this. All right. And now by using k-means, we can determine outliers. Now let's say suddenly there's only one group, or there's 3 groups of spending for you, right? Now suddenly there's a 4th group which is very far from all these 3 groups. Based on the distance calculation, we can deduce that this thing that you just spent on is an anomaly. It's something that you don't normally spend on, which means that your credit card might have been stolen. You get it? So that's how you can use k-means on a real life application. That's just one example. There's actually many examples out there. Now the only problem with k-means is you have to know how many groups are you going to separate this data into. I mean, for example, with the same data, let's say I only separate this into two groups. I didn't know the existence of a third group, let's say. So no matter how many times I update the centroid, it's going to be like this. So half of these Chinese people are going to be categorized as one group with the European, and other half is going to be categorized one group with the Indian. I mean, obviously, depending on where the centroid starts, right? I mean, if the centroid started at a different area, then we probably end up with a different uh, see, we probably end up with a little bit of difference in the classes. So this time all the Chinese and Indians are one group and this person is one group. So a bit of difference is there. So that's another limitations of K-means. The starting point is quite important when you don't know how many groups are there. If you already know how many groups are there, then the starting point is not a big problem, right? So that's a little bit of a limitations of K-means. So let's try a different example. So let's try our smiley face. So we know there's 1, 2, 3 groups here: eyes, mouth, and the face. So 3 groups. Let's see what's the. There you go. Not quite what we expected, but obviously, according to our logic on how the k-means work, this is a plausible uh, outcome, right? I mean, we have these clusters as the green, and these clusters as the blue, and these clusters as the red. It's just a mere distance calculation. So how is it going to know that this entire ring belongs to one group, and this two belongs to one group, and this one belongs to one group? I mean, this one is fine. This one looks plausible, but these two, no, not really, and this entire ring, not really. So this is another limitations of k-means. It just looks at the distance. It doesn't look at the pattern of the data. There are a lot of other algorithms out there that actually looks at the data, like dbScan or even mean shift clustering and so on. So this is just one example of the limitations. Now let's try, I guess, two. That's it. That's nothing fancy going on there. Right. So let's just add as much as we want and go. There you go. Yeah, not quite like what we expected, but according to our procedure that we went through, this is again another plausible explanation on what's going to happen. I mean, the outcome, right? You see that the points are evenly uh, apart from each other. I mean, their distance against each other. There's no 2 points that are very close by together or very further apart, right? I mean, they all have their own groups. So this is how just one example of k-means works. Now, let me show you one real life example of k-means segmentation. All right, we can also use it for image segmentation. Now, what does that mean is this. So you have this image over here. It's just an image of a flower with some background. And when you when you look at the data points, obviously images are made of pixels, right? So there's R, G, and B. So red, green, and blue. That is also a data point, right? Each pixel. So when we plot them, it looks somewhat like this. Okay. Now, when we apply k-means to cluster them, these are the clusters. So red color at one area, the bright red at one area, brown is one, orange, yellow, white, and so on. Now, when I reapply them back to that image, this is what I get. So from this, it became this. So you can see a lot of those colors were averaged, like the green at the back looks like a palette green, it looks like an oil painting, right? So this is one more example of image segmentation or of k-means being used for image segmentation. Now, why is this important? All right. Now, let's see one application. Let's say that you have you have this need to look at a person's image, face or whatever, and you need to determine their skin color. Okay. Now, how would you go about that? I mean, obviously, you can just write an algorithm to detect their face and then take the skin color from their cheek, or maybe from their forehead, or from their nose, or whatever, right? But what if there's shadows in the image, or what if the person has a burn mark on the cheek? So now your algorithm's going to be off, right? I mean, you're not going to be you'll never be able to figure out what's the uh, their skin color. What you can do here is apply a k-means first. Now, what's the k-means going to do? It's going to group all of the skin color together because they all look similar to each other, right? Something like this over here. So you see all the skin color over here is exactly the same, even though there was like a little bit of deviation in the skin color. There's a bit of a toned dark over here. But again, it's going to take the average, right? I mean, it's a clustering algorithm. So it's going to take the average over here, and then it's going to apply it to the skin, just like what we saw with the uh, with the with the flower over here. So you can see at the back there, the green, it became one single color, the average of it, right? So that's what's going to happen here as well. Now, once you've done that, now you can use your previous logic to take the skin color from the cheek or from the forehead, from the nose or whatever. It's going to be much more accurate because even there's like a slight burn mark or a little bit of shadows and all, those things are going to be averaged off. Okay, so this is just one example of image of K using k-means on an image segmentation. But in reality, there's a lot of stuff that you can do. Okay, all right. So far, do you guys have any questions? Is this used for image denoising? Yeah, that's a good question, Cornelius. I think yes, you can use it for image denoising as well. It can be part of a bigger picture. You can use it in the early stage and see if the noises cancels out. If it doesn't still, then you need to use other algorithms because this can be applied for simpler images, right? With not so sophisticated background, with some with very very plain kind of background or very plain kind of clothes, those kind of images, you can use these k-means to cluster off. But if you have a very complex photo with a lot of colorings, then it's going to be very hard because you're going to lose a lot of other informations. Yes, of course, you will be denoising the noises, but you're also going to lose a lot of your original pixel values, right? I mean, that's one thing that I can think of from the top of my head. For example, in this picture, right, over here. So yeah, we might have some noises over here, and when you use k-means, the noises are gone, but obviously the features that makes up the grasses, the colors, they are also gone, right? So if it's a very simple image, then with very plain background, then yes, it will work. So it depends on the use case. Yep, correct. Some of the visual information is also lost. All right. So let's try to implement this entire thing using nothing but NumPy. So we're not going to be using any libraries like sklearn or OpenCV or whatever. So we try and apply our logics into the implementation. All right. Okay, let's. All right. So these are my codes, like I showed earlier. So what I will do, I'll run one by one for you guys to see what each of these code blocks are doing, and then I will explain to you guys what each of those lines in the code does, right? So the first one is nothing important. It's just importing the libraries. I might not have the mplot 3D. I do. Okay. All right. So this is just me setting the image height and width. I do need this image too. Let me see if I have the image. Now I can just use a different image. Okay, seems good. Okay, let's make it a bit bigger. Okay, a little bit more detail. All right, so basically what I've done here is I am using the OpenCV library. For those of you who are not from a computer science background, uh, this OpenCV library is a computer vision library. So it's very helpful for you to manipulate your images, to load your images, to save your images, things like that. Right. So it's basically just some image libraries. All right. So what I'm doing here is I am reading the image which I just saved, and I'm converting the color to RGB. Now, by default, this library reads an image in BGR, okay, blue, green, and red. Supposed to be RGB, right? I mean, for some historical reason, it's in BGR. Okay, so that's why I'm converting the color back to RGB from BGR, so you don't have to mind too much attention to this detail. And what I'm doing in the second line is resizing the image to image height and width that I set earlier, which is 1024. The reason why I'm resizing is because the original image tends to be really big, and if it's really big, then the k-means clustering is going to take a lot of time because there are more pixels in it, right? I mean, more data points, obviously, when you have more pixels over here, right? So this is just show you, this is just the code to show the image for you to see, right? So it's over here. Okay, now let's see the pixel values. Okay, so what I'm doing here is I am reshaping those image to the reshaping the image um, to sorry to a different to the channel, the R, G, and B. So it's basically just there are three image, and then there's just one over here. There are three channels over here, right? R, G, and B. And then I'm just checking out the pixel values over here. Just one of it, okay? So I'm just checking the zeroth index. If I obviously print like this, then there's going to be more at the fourth value, all right? Okay, now let's try and visualize all the pixels that we have so far. And it's going to take some time because our image is actually quite large. There you go. So there's a lot of image, a lot of data points that we have here from this image. Let's try and reduce the size of it. Okay, a lot faster. Okay, so we still have a lot of data points, but okay, we will just work with what we have right now, right? Okay, so unfortunately, this is not interactive. Okay, so we have three dimensions over here. Remember what we talked about earlier? We have the skin tone, the height, and other things that we are other features that we were looking at a human, right? So same thing here. We have R, we have G, we have B. Now it might be different. It might be G here, R here, B here, but it doesn't really matter. So what matters is that we have 3 dimensions over here, and each one of these pixels represent their place in these 3 dimensions. Okay, so that's how we visualize. It's a bit different from this image though, because this image has more green, mainly dominated by green. So I suppose that's why there's a lot of data points in this area over here. Okay, so now we are going to build our k-means class. Okay, so this part I might need to take some time to explain to you guys. Okay, now the first is obviously we're going to initialize some variables, so nothing fancy is going on here. Okay, so the first is the number of k, the number of clusters. Okay, so that's going to be represented with k, and then obviously this is just some data points, and then we want to see how many rows are there, and then these are the centroid later that we're going to be picking up. Okay, and then okay, so the centroids are randomly determined from here, from the data points. Sorry, it's not random. It's just gonna choose the first few data points. So it's gonna start probably somewhere with the first here. So if you choose 5, then all 5 of them are gonna be somewhere here or somewhere here at the corner, whichever the 000 is, right? So that's where the centroid is going to be starting. And the distances right now are empty. So we're gonna keep all the distances from. Remember that we need to keep track of each data point to the distance between each data point to their centroid. So we have to keep the record. Only then we will be able to find out what's the lowest distance or the least distance and then assign the data point to that particular centroid. Okay, so that's why we have this part. So this is just the normal distance calculating algorithm. So you don't have to, for those of you who are from the non-computer science, you don't have to be afraid of this kind of fancy lines of codes. It's just as easy as just Googling it. For example, this one, when I Google it, there you go. So it just straight away gives me what this function is about. So this function is is returning the norms. Norms, in other words, is actually the distance of that particular 2 data points. Okay, so the reason why we are using all these fancy words is because it's from linear algebra. It's just some mathematical fancy words. Okay, so but without all this under the hood, it's just a distance calculation. Okay, so why the reason why we are using such library instead of doing the Euclidean distance by ourselves is because we are using we are kind of utilizing the vector here, vector and matrices instead of just normal numbers, right? So that's the reason why we have to rely on the NumPy. All right, so this part is where the magic happens. All right, so while this part is while the so this while loop is going to go on forever until the stopping criteria is met. So the stopping criteria is met when all of those last centroid, when there was no more update with the centroid. So it just stops when the centroid is not moving anymore, when the average is where it is, right? So that's the breaking criteria over here. So that's what you need to know about this while loop. Okay, so the first thing it does is it goes to the it calculates the distance between the data points and the centroid. The reason why we have rows is because of the RGB. Okay, so we calculate the each distance between the RGB over here, and then we take the nearest centroid. How we are using the nearest? How are we determining the nearest centroid? Is using this NumPy argmeans function call. Again, you can just look it up on Google. Returns the indices with the minimum value. Okay, so there's nothing fancy going on here as well. So all we're doing is remember the distances that we kept in a record earlier. Yep, so that's the distance row that we are using to find all the nearest centroid belonging to that particular data set. Okay, so now we have the nearest centroid. we don't have any last centroid. The last centroid is down here, so this stopping criteria is not going to work. It's none. Now here we go. Now we need to calculate the mean of the clusters and then reassign back the value of the centroids. So for each of those clusters, right, in the K, if our K is 3, then it's going to be starting with 0, 1, and 2. If our K is 4, then it's 0, 1, 2, and 3. Okay, so this is just a simple for loop. Now we're going to find the mean. How are we going to find the mean? We take all the data point and then the one that we assign to the cluster with the nearest centroid. Okay, for example, in the first loop, this cluster is going to be 0, right? So we take all the data points that has 0 as their cluster, that are closest to the 0, and we calculate their mean. Okay, again, you can look it up, the mean. What does this mean? There you go. Compute the arithmetic mean along the specified axis, meaning that it just finds the average value. Okay, so we take the mean, and then we take the cluster, the centroid and the centroid that belonging to that cluster, and we update their position to the mean. Okay, so this is where the reassigning magic happened. Remember this part when we restarted and we added 3 centroids, and when we update, okay, this particular process, right? This is what's happening over here. And now what we do, we update this last centroid variable with the nearest centroid. Okay, now in the next iteration, it's going to do this reassign and then update again. It's going to reassign, update again, reassign, update again. It's going to continue until there's no more updates. Okay, so this is our stopping criteria. So it stops when there's no difference between the nearest centroid and the last centroid, meaning the last known position is where it is now. Okay, so there's no difference when all 3 centroids reach it. That's why we have this all over here. Okay, so we stop it, and now we return all the nearest centroids and the centroids. Okay, so we're gonna run it. There you go. So it's still calculating over here. Kernel busy. So we have centroid index. Let's see what is this. It's gonna take some time because there's too many pixels there. 512 times 512. So there's a lot of pixels. And remember that you are just calculating the distance to all the centroids. And I'm using 8 centroids over here. Yeah, I should have maybe used lesser, but it's fine. Let's see. So the data points are the pixel values, and the K is 8, and it will return us the centroid index and the centroid from the K means over here. Okay, while it's running, up to now, do you guys have any questions, or do you want me to clarify anything? Alright, I guess that's a no. I think I'll just try and reduce the size of the image because this is taking too long. Alright, there you go. Okay, so you see the centroid index. We have the numbers of the index of each one of those data points, right? And these are the location of the centroids that we have. So remember, we said 8 centroids, right? So let's see if there's 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there are 8 coordinates that we have here. So remember, this is all happening in 3D, okay? So that's why we have 3 coordinates representing the centroid's position. So this might be R, this might be G, this might be B, RGB, or X, Y, Z in a simpler terms, okay? and you can see the clustering over here. See how it is, how it looks like. So this is one particular cluster, this is cluster, and there's one in the center and one at the side, and these things over here belongs to each in the red and this orange zone over here. The color here doesn't represent the color in this picture. So these colors here are just some mapping, labeling kind of thing for us to see, like a heat map, okay? So for us to see the differences. So don't get confused by this. So the same thing actually, I'm just using the pixel values over here, like how I did here. Just that the point is, I'm now using the centroid index over here at the C. Okay, so that's the only difference over here. Now let's see how this affects our final image. All right, so I'm creating new image. Okay, so it's just NP zeros, so it's just filled with zeros with the same of the image I had here. And based on the centroid, I am taking the average of each centroid and the position over here, and then filling them up with the average color of the centroid. Okay, and once I have that, I just reshape the image so that I get back, I'm reshaping the array so that I can get back the RGB channeled image. And we're going to show the image right now. There you go. See? So this was our original image. And now we have our segmented image like this. So as you can see, like the clouds, white color is mostly segmented with white color, and the shadow underneath the cloud, like a light blue kind of thing, is segmented. And then the water is the greenish water. So we have all the green color over here, the sand. So it made the picture much more simpler. Yeah, it looks animated like an oil painting, right? So that's it's just one way of using K-means. You can use it for aesthetic. You can use it for many different purposes. You can be creative as you want. Like I said, the face, um, the skin color, right? Recognizing the skin color of a face. It's not necessarily that you have to use K-means before you determine the um, skin tone, but it's better if you use K-means so that it gets average. For example, let's say you want to determine the color of the sea over here, right? You start here. So where would you look for the color of the sea? If you look at the wrong place over here with the shadow, then what's going to happen? Or maybe you look at this place over here. So it's a bit of yellowish, right? So now you get a inaccurate kind of a color for the sea. But when you do K-means, now you see it's average. So the risk is lower. Obviously you can still look at here and then get the wrong shadow color. But you can see here, right? It's mostly greenish over here. So when you point it to any one of this pixel, you can get the green color. So you get the average of the sea color. Obviously there are 3 average over here. Okay. If you want like a better average, then you can just reduce the number of K over here. Maybe if you reduce it to 4, let's see what happens. Okay, there you go. So it's way more off than the original, but at least now you see the color of the sea. You get a bit more of the average of the color, right? So there's no more um, all these foreign colors that are not supposed to be there when you get the color of the sea, right? So from here, you go to here. Yeah, obviously you like what Cornelius asked earlier, you can use this for denoising, but you lose a lot of information over here. But again, it depends on your use case, right? What are you using it for? This is just one example. The fraud detection, the credit card fraud detection that I gave is another example. You can also use it for like denoising the image and anomaly detections, even just randomly clustering a group of data points so that you can, you know, reassigns them, or you simplify the data, things like that. So you can use it for many different purposes. Text clustering, I'm not really sure, but I bet you can when you have the word embeddings. What I mean by word embeddings is that if you study about language models, you have vector representation of words. Yeah, aggregating articles of different topics together. Yeah, I mean, why not? Like I said, you can use the language embedding first, word embedding, sorry. You use the word embedding to embed each words into vectors, and now you suddenly have all these similar vectors together, right? Now you can use k-means to, yes, correct, word to vec, word net, those kind of things. You can use those output from word to vec to cluster them into categories like crime novels, romance novels, comedy novels, things like that. But obviously, you wouldn't know the name of those books. You have to name it yourself. It's just that it will help you to group them together. And when you have a new book coming in, based on the genre, like romance, whatever, comedy, it can put it into the correct group, right? So that's means it's a very simple algorithm, but still it is used until today. And there are a lot of variations of k-means out there. I mean, they have better. I mean, earlier we saw a lot of limitations on k-means, right? So there are also some method to determine how many centroids that we're using. I mean, one of it is called elbow method, if I'm not mistaken. Let me see. There you go. So the elbow method is a graphical representation of finding the optimal k in a k-means clustering. So it's kind of like a trial and error, but a smarter trial and error, I guess. So elbow method is also kind of an old method, I suppose. So there's some sort of a controversy going on here, but it's written in 2022. You can take a look at it if you would like. But here's how you see which number of k is the most optimal for you. So you can actually explore these kind of things when you are doing k-means. Again, it's a very simple algorithm, but super useful, something that you would want in your bag of tools, obviously, right? So far, do you guys have any questions? While you guys any questions, I'm gonna run this. How about those silhouette coefficient? I've never heard about that before. That's really interesting. Thanks, Cornelis. I'll take a look at this as well. Sure. All right. How about you guys that are not from non-computer science background? Do you guys have any questions? Not much. Mhm. All right, so since there's no question, I'll just talk a little bit about its application and we can end the session from here. Um, there you go. So anomaly of fraud detection, inventory categorizations, environmental risk, pattern recognition images. Yeah, that's also a very good um, application of k-means. You can actually group them into two or three categories. Like for example, in this is segmentation of blood cells for leukemia detection and to detect infected fruits. So you can always have multiple groups, two or three groups. And suddenly when you give an infected fruit and it belongs to this particular group, then we can classify that as a infected fruit, right? I mean, basically it boils down to the classification algorithm now. So from clustering, you can also use it as a classification algorithm. And the best part about all this is, right, guys, it needs no label. So there is, that's why it's called an unsupervised algorithm. Like the earlier example about you being an alien and coming down to look, some of you answered that you can't differentiate because you are seeing people for the first time, right? Fluff. Fluff answered that. Now, the thing is, you don't have to know, you don't have to see the humans more than for the first time. I mean, the first time itself, you could see all the facial uh, features difference, the skin tone difference, the height difference, and so on. And you can immediately categorize them into groups, right? So you don't have to know any other information. So that's what unsupervised algorithm is for those who of you that are confused. What is supervised, what is unsupervised, semi-supervised, and so on, right? So this is what unsupervised is. You don't need to know the label of the data to label it, right? So that's what k-means does for you. It's an unsupervised algorithm. For supervised algorithm, most of the time we're gonna have labels on them, and then our algorithm is going to map those labels to the features of the data. And then now when a new data comes in, it's going to look at the features and then map it to the label based on whatever that it has learned previously using the data, right? So that's one interesting application of k-means as well, and it's a great strength of k-means as well to be unsupervised rather than supervised. Okay, so that's about it. If since you guys have no any other questions, I think we can end the session here. If you guys have any other questions that popped up in your head even after this session, feel free to just message me, and you can always ask me for those questions. I'll be happy to answer you guys, right? And if you need more clarifications for this as well, please reach out to me. All right. Thank you very much, guys. Have a great night, and I'll see you guys in the next session. See you guys. Bye.